adjust that. So come back over to the project editor for a second. All these different surfaces basically are floating around with some sort of thermal properties. So for each of these different properties that are kind of hanging around out in here, for example, let me go to the 3D editor, escape out of there, and choose something. For example, that wall actually has some thermal properties, and we can go through and actually take a look at what those properties are. So right now it's something that's considered a brick timber frame wall. That brick timber frame wall actually has some thermal properties, and you could actually dig in there and actually find out what the U value is. This U value that's actually associated with the brick timber frame wall is actually pretty bad. In the scheme of things, it's 0.31. This is one that really doesn't have very much insulation in it, because if it had any insulation in it, we could actually bring it down quite a bit, as opposed to 0.31. Down to 0.07 or even 0.05 or something like that. So the model right now is really pretty much an insulated wall. If we wanted to go through and change that to a different type of wall, we could. You see there's a lot of existing wall types they have hanging around in here in this tool. Things like rammed earth walls and timber-clad masonry. We have all sorts of different stuff in here. But if I go back to that brick timber frame or something like that, and I want to go through and basically kind of change that, I can go through and change its properties. If I wanted to make that more of an insulated wall, I could do something like just put in the U value. So for example, if I put in a U value, which is more common with our 13 insulation we'd use here in Northern California, let me just round it off to 0.08. Close that up. We can also go ahead and take a look at the roof. Don't forget the roof. Right now, the roof is actually something made out of just metal deck, uninsulated. Notice it has an incredibly high U value right now. Okay, 1.25. Again, if we insulated that, we put some sort of roof insulation in there to lower that, we could really lower things. So, yeah, does anyone know what the amount of roof insulation you're supposed to put in for this area is? You know offhand? Like via Title 24 standards, if you're going to go through and do a house here in Northern California, kind of on the Stanford campus, something like that, you're basically going for an R30 kind of roof construction. So for my friends in the back, actually even 1/30, I could probably figure this out. 0.3 something or other. What's that?
0.0.
Thank you. Oh, that's right. I'm going to get myself in big trouble then. Okay. So if I was going to go through and make that more insulated, I'd go ahead and something like that. Apply those changes and close. And let's go ahead and try rerunning our analysis here. So here we have heating in St. Petersburg. We're looking at this, what? 214, 841, 392. So 214 million BTUs or something like that. We've just changed the thermal properties a little bit. Okay. It went from 214 million to 31 million 5. Okay, so huge difference in terms of changing those thermal properties. What we've really done is we've really cut into the conduction. Okay. Changing the U properties really changes the conduction of something. So even if we now went back and looked at that thermal analysis in terms of what's going on here, if we look at the conduction, okay, and the percentage which it's the heat that's actually being lost, it's actually relatively small. Actually, at this point, we are losing more just through ventilation of the space than we are actually through the conduction. Okay, so conduction change, or R values changes the conduction. That's really one way we can sort of approach that. Let's talk about some of the other ones. Direct solar, we're going to get into that. For windows, as we're looking at different parts of our windows, every window is rated in a couple different ways. Windows have the notion of not only a U value, how much heat flows through them, okay, and window U values are actually getting pretty good. Actually, you have a good sense of really, what's a good U value for a window? Do you have any sense of that? They actually have windows now, they're right around 0.3. So on this scale of 0.05 and 0.07, kind of around 0.30, something like that. Not too bad. Not as good as a fully insulated wall, but not too bad. they can actually get windows that are much, much even better. You know, they're getting them down to 0.20 and 0.15 and things like that. So you can really get some very nice high performance windows that are almost as good as walls. And those will address the issue of conduction. There's something else, though, you need, which is something called the solar heat gain coefficient. And that's all about the amount of radiation that's flowing through. So we can decide whether we like the radiation flowing through, because it's heating things up, or not. You know, and that's actually a window property we can specify. Let's talk about the last chunk, which is this direct solar radiation, because that's actually kind of an interesting property. Let's think about where that applies the most. So as you look at this building, okay, and the surfaces that are floating around in here, you know, which surface is it that you think actually has the biggest impact from the solar radiation? Right now, is it the walls or is it the roof? What actually gets the most sun? Yep, the roof by far gets far more sun. We can look at all sorts of solar radiation profiles, and it's just got sun almost all of the day. We're almost any other surface. It gets part of the day, and the sun moves around, and it does all those things. Yeah, the roof gets it really, really bad, and there's a lot of solar radiation. So, yeah, as we think about roofs and the amount of solar radiation they actually absorb, you know, what are the factors that affect how much solar radiation you absorb? Like, you know, what do you think affects how much solar radiation actually gets through a surface? Like, of all the different properties. Is the texture? What's that? Reflectivity. Reflectivity is a big one. Yes. Yeah. And reflectivity is probably the best way to say it in terms of what's going on. Another way that's kind of simple to say is just in terms of the color. Okay. But reflectivity is truly the issue because it really gets to, you know, if you have a surface which reflects an awful lot, then the radiation won't get absorbed. If it doesn't reflect a lot, then a lot of radiation is going to get absorbed into it. So if we were going to just relate that from reflectivity back to a color spectrum, you know, what color is the absolute worst or best, depending on how you look at it, in terms of absorbing a lot of radiation? Exactly. Okay. What color are most roofs? Yeah. Warehouse, yes, they're almost all black. These black tar roofs with some gravel and stuff like that. They bring in an incredible amount of solar radiation, which can be very, very good for you or very bad for you. Or depends on what time of the year it is. Okay. If you wanted to go through and make the roof absorb an awful lot less energy, okay, through solar radiation, you know, what color would you make it? Yeah, just a light color, like white. Even white's a really good color. So when you hear people talking about cool roofs and cool roof surfaces, they're almost always these white reflective roofs. It's all really a notion of trying to keep as much solar radiation from reflecting in as possible. Even if you're going to go through and you're going to reshingle your house, you have your house, it needs a new roof, and you're choosing different shingle colors, you know, that has a huge impact. If you choose black shingles, they absorb a lot more energy. You have a very hot attic, which can be good or bad, again, depending on what your temperature profile is. If you have white shingles, they're going to reflect an awful lot. Okay, so color's huge in terms of what's going on. So let us kind of take this sort of thinking and roll back to sort of more of a building model and think about how we can apply it there. Because, you know, the same sort of things actually play out like in these little structures here. Good. You got the basic principles. It's all about conductivity. It's all about, you know, the solar radiation absorption or the reflectivity in terms of what's going on, you know, and the amount that's actually passing through. So this little building over here is a pretty boring little building in terms of what's going on, but let's start thinking about its properties. Okay, it's not very pretty right now, but even as we go through and we look at these walls, these basic generic walls, we can start thinking about and adapting and making sure we're modeling accurately relative to these things and incorporating those in our design. So here we got this wall. Let's kind of hang it around a generic wall. We can take a look at its properties. And what's going on in here? There are some properties about the absorbance, the roughness, the heat transfer coefficient, or thermal resistance. Right now, those are going to hang around blank. The reason they're hanging around blank, it's kind of a generic wall. We don't really have any specific materials associated with it. Okay? But let's go ahead and change that. If we go popping over instead and we say, let's see what we got available in here. Well, we got this nice exterior Eifs wall. That's kind of a metal stud system that has like basically a foam insulation and almost like stucco on the outside. Take a look at that. That has a thermal resistance of about 66, which is pretty darn good because my wood frame walls that I'm typically building in houses are like R13 or R19. It also has this heat transfer coefficient of like 0.01. So as a wall goes, this is an incredibly tight wall. That's really very, very little conductivity coming out of that. Switch over to some other ones. Oh, if you did like a brick wall, okay, the thermal resistance is only about 1, something like that. That's not very good in the scheme of things. If I go through and I change that to more of a CMU wall, actually, let me do brick on CMU. That's brick on concrete blocks, concrete masonry units. Okay, 2 layers. Okay, with that, that's up to 31, so that's not so bad in the scheme of things. If I go through and choose something like CMU insulated, okay, it's interesting. That's only 26. But let's talk about where it's actually getting these numbers, because these are all kind of perfectly controllable. Okay, so the way it actually works in terms of computing the thermal resistance of a wall is that there are different materials that have resistance and density to them, and basically it works that the thicker the layer of that material is, you get to sort of linearly scale up what the resistance is that's added by that layer. Okay, so let's think what that actually means. So if, for example, we take this CMU insulated wall, let me go ahead and take a look at its properties a little bit. And I edit it. You'll see it's got a bunch of different little layers in here. It's got some concrete masonry units. It's got some rigid insulation that's 3 inches. It's got some damp proofing. It's got some concrete masonry, some metal furring. It's got a number of different things here. Okay. As you look at that assembly, really, which is the layer that you think makes the biggest difference in terms of just the thermal resistance right there? So of all those different layers, which is the one you'd target for thermal resistance? Yeah, that's probably it. So let's take a look at how that's defined. So I got this rigid insulation. I can take a look at the properties of it. It actually has all sorts of properties. It has appearances. It has kind of what it's going to look like when we render it. We've been paying attention to some of those things. But it actually has physical properties too, in terms of like a thermal expansion coefficient, what the mechanical strength of it is, what the yield strength is. It also has thermal properties. Okay, so it has to it right now basically a thermal conductivity or thermal resistance as well as reflectivity. Yeah, it's really kind of based on, it's all based on densities. So as we go through and scale it up, we should actually see it's BTU per hour per foot per degree Fahrenheit. Let's see if it makes sense of that. And there's the density. See, you munge all this together. So basically, I got a rigid insulation layer right now. It's 3 inches. Okay. Right now, that rigid insulation layer, along with everything else, is basically delivering a wall with essentially like an R26 value to it. Okay? So if I wanted to go ahead and raise it, let's see how big the impact is. If I go through and change rigid insulation from 3 inches to, let's say 4 inches. See what how big a difference that makes. It's not a very big difference. Okay. What was it before? Was it 30 or what was it before? 26. 26. Oh, so it looks like it raised it about 4. Okay. If I went through and raised it to 5 inches, what do you think, how much higher do you think it's going to be? About 34. So it looks like we're getting basically an R value of 4 for every additional inch of insulation. Okay. So we can design a wall really to go through and have whatever level of thermal resistance we want just by adjusting its thickness and putting a thicker layer of rigid insulation on it. Okay. That's actually pretty good in the scheme of things. So I could go through and as I'm modeling, I want that to be a brick wall. Let me go ahead and change this and I'll make it that same sort of wall. What was that? CMU insulated? Got it. Let me pop those around. In fact, I'll just do a tab to get them all. CMU. Now, let's think about this. I've got these fantastic walls. They're hanging around here with this thermal resistiveness of, what do we decide here, somewhere around here? It's around 34 or something like that. Okay. I got this roof surface on the top. Okay. How should the resistance of the roof surface relate to the resistance of the walls? Yeah. Should it be the same? Should it be less? Should it be more? What do you think? Yeah, you can argue about this in terms of really what it is. You sort of know that relative to Untitled 24, based on what I told you right now, there seems to be this notion of like making it higher. Okay? It often has to do with this whole notion of really, the amount of roof surface there is on the building and how heat's trying to rise and go out through that direction, through the space. Often we try to make it higher. If nothing else, it should at least be as good. It makes no sense to have a roof which is very poorly insulated and walls that are very strongly insulated, because then, your system's only as good as your weakest link. Is really what it kind of comes down to. So if I had super insulated walls and a weakly insulated roof, I'm not going to save that much. I'll save what's going to go through the walls. Okay. But if I really want to go ahead and design an entire system that's going to work together, I should take a look at this roof too. And as opposed to a generic roof, we can take a look at some things in here. We got all sorts of things in, like a steel truss roof with insulation. Let's take a look at that one. Edit it. And the same basic thing is going to apply here. What's the thermal resistance? Wow, 113. That's super insulated in the scheme of things. Let's take a look at, just like more insulated wood rafters, like wood rafters on a typical house and insulated. Okay, around 57 or something like that. So we can decide what kind of roof systems we want. But what's going to happen here is, because we're putting these thermal properties in here, all of a sudden, the energy use that we're using is going to greatly kind of reduce itself. So let me kind of do that and talk about what this means about as we're modeling and how we have to get started. The problem with so many of the tools we first use is you put geometry in there and you send it off and you immediately do analysis and you don't bother to kind of stop and pause and take a look at really what the thermal properties are. You just got to do it based on the shape. And actually, the thermal properties and the shape have to sort of work together to kind of really achieve the right balance. Yeah. There really is this funny relationship about conduction and for the radiant surfaces that are coming down that all has to work together in that. Really, from the outside of the space, all around, and from the roof, you have this temperature differential, so heat's going to be flowing in or out, really through all those surfaces. In the same sense, solar radiation is going to hit some of these surfaces and try to be coming in through those, and you have to adapt the properties of those. Now, as you think about this, think about it, just a little bit different. There is this whole notion of shape and really what the properties should be relative to the shape. So for example, let's think about this just ever so briefly. Yeah, if we were going to go through and kind of create a shape of a building and even allow that we're going to kind of do thermal properties right, the question is, are there better shapes of buildings than others? I think some of you have heard me do this already, but let me just kind of like lay it out for you. So for example, if I wanted to encompass the same amount of space, but do it in different shapes of the buildings, really, the notion is really, what's going to be the most favorable approach towards doing that? Well, in fact, you can already start to talk about it. If there's a sort of a relationship between the volume, okay, that you're trying to encompass in space, okay, and really all the surface area has the potential of either gaining or losing heat, okay, really. What shape would I create if I actually wanted to enclose the maximum amount of volume with the least amount of surface area to gain or lose heat? Okay, so what shape actually has maximum volume for least amount of surface area? Yeah, it's either a circle or a sphere. Okay, so that's actually good just because of the radius and the relationship there. That's actually one of the most favorable shapes. Now, sadly, it's actually kind of hard to build buildings that are spherical, to actually truly optimize that. We can do nice towers that look like big tin cans or something like that. That's actually a pretty good shape in the scheme of things. But if we can't go ahead and work with kind of rounded surfaces, if I had different shapes and I was trying to encompass the same amount of space, you could think about there's a lot of buildings that look like this. Okay. Very long, flat, not very tall, kind of squatty buildings. Okay. You have a lot of buildings that look like this. And then you have some buildings which are somewhere between. Okay. So given those three shapes, relative to the issue of the conduction through the surface and the amount of surface area, if those three shapes all encompass the same amount of square footage and floor area, which of those buildings do you think would actually be the better energy performer? Any votes for others? Let's talk about it. What's wrong with this shape? What's the problem with that shape? Okay, tall office tower, you find this all over the world, especially in very dense urban environments. We build these really tall little towers and stuff like that. So from an energy standpoint, what's kind of hard about this building? Just from the standpoint of surface area to amount of square footage. Okay. Just as you look at the tower overall, you think about it, there's really a lot more skin on this building per square foot than really almost any other shapes. This has an awful lot of surface area to it. Okay, that's exposed. So all this surface and all the size is constantly exposed to the weather and the changing temperature and stuff like that. So if you're here in the middle here, it's really hard to get away from the weather. It's like no matter anything that happens, you're almost immediately affected by that. So this is actually kind of a very tough shape. We build buildings like this because in the grand scheme of everything in sustainability, when land is very precious, we often have to build vertical cities and do stuff like that. So there's a lot more of this than just energy use. Energy use is just one piece of it, okay? But these buildings tend to be hard from an energy standpoint. They're good in every standpoints because as we all live in this vertical city, we probably don't all drive cars and have huge parking lots and everything else that we do that also impacts the environment. This kind of building is kind of an interesting one. It also has a fairly large amount of surface area to it. Okay? But what kind of surface area does it have? Okay? It has a lot of roof, and it has a lot of floor. Okay? And those can be good and bad. The floor is actually considered, in the scheme of things, a relatively good surface area because it's considered inert. So for the most part, it maintains a constant temperature. It's kind of viewed as being a very favorable surface. Okay? We like the floor, or the earth, because hugging up against the earth, it tends to maintain a fairly constant temperature. We don't lose heat. We don't gain heat through it. It's considered a good surface. The roof can be good or bad because it absorbs an awful lot of solar energy, okay, depending on whether it's a cool roof or not. But, that's also a shape that we see an awful lot of, and it tends to be not so bad. What saves it, like this one gets the double whammy. It has very little earth and almost all exposed surface. This one has a lot of earth, a lot of exposed surface, but somewhere in between. This one, you could say, is kind of one of the optimal shapes. What'll tend to happen is, it's got the earth, it's got that. What'll typically happen is one of these will win. If we looked at it strictly from energy performance, it just sort of depends. Sometimes either one of those shapes will win. But it's just generally when you get closer and closer to this, that's where you start getting into more and more trouble from an energy standpoint. Okay, so for what we want to think about relative to the building modeling, as we go through and we start to design surfaces, we go through and put our building envelopes together and we put in there, we have these walls, they have conduction and all that kind of stuff. Then we're going to go through and put in windows. And as we go through putting in windows, they also have U values. See if they actually list some of these. Yep. Even for this window, it's looking like this has a U value of 0.64. That's not the most efficient window. We'd like to get a much more efficient window than that in terms of what's going on. And we can find a more efficient window and drive that value down. But relative to that right now, let's just kind of think about it. For each and every one of those windows that I put in there, if that's 0.64 and this wall over here is 0.02, basically each and every square inch of that window is going to be conducting 30 times as much energy as the wall. Okay, so we really have to pay attention to those windows and hopefully get ones that have a much better thermal coefficient in terms of what's going on. We can also go ahead and put skylights in this building, in the scheme of that. Oh, let's go ahead and, where are they? Do they live under skylights? I don't remember windows. Let's see if they're even hanging around in here. I think I have to go load them up. But they have the same basic property. Skylights are basically just roof windows. If I go out and find skylights, oh, that's interesting. It wants me to load it as a window. This is that whole thing about curtain wall doors. People have heard me rant on that for too many times. Okay, it needs to load as a window, even though it's a roof window. It's from that folder. Blah, blah, blah. Skylight. Oops, did I do the wrong thing? I think I just did the opposite of what I said I was about to do. It wants to load as a component, even though it's in the Windows folder. That makes it even more insidious in terms of what's going on. Okay, so component, place component. You gonna let me do it? Now it's going to completely vex me in terms of what I'm doing. I got component. I got that. I need to sort of load a component. What's happening is there's actually some things over here on the side that you can't see because my screen's too small. Let me try loading it that way. Nope, it wants to be a window. This program exists largely just to kind of vex me. Let's see what's going on. Right there. Okay, now you finally did. It wants to load as a window. We'll put some skylights in there. They have all sorts of daylight advantages we'll talk about, but even they have thermal properties. If we go through and take a look at them, yeah, that's got to be, again, about a 0.64. Pretty much the same as a window, and that actually sort of makes sense. It's mostly glazing, it's mostly framing. In terms of the conductance, conductance doesn't really care a whole lot whether it's going up through the roof or going out through the walls. It's pretty much just a window, okay? So we need to kind of start looking at those. But basically in the same sense, if that's 0.64 and this roof is, what is it, 0.01, okay, again, we start to see an awful lot. We've put skylights in, we're going to enjoy fantastic daylighting advantages, but then I have to do something to go ahead and kind of guard against the thermal effect of the skylights. So we'll talk about that some more. So let's go ahead. We will stop for there tonight. You know, just in terms of creating the envelope, the big thing to get out was this whole notion of the conduction, and really for the conduction, how we actually go through, put things in the building and start to control the U values for the envelope we're putting together. What we're going to talk about next time is actually, given that we're starting to build envelopes out of something like this, how do we actually start articulating the architectural form a little bit more to moderate some of that stuff. So we'll look at, for example, in a curtain wall system, how we can do fins and shelves and things like that to add a little bit of architectural detail that actually work with it, so it's not just the big box conducting things, but we can actually control that amount of sunlight through architectural features and really kind of work a little more creatively to kind of give us things that have a little more sophistication to them. Okay, so let us break for today, and we will keep on going next time with really more about just like kind of the architecture and how we take these things and again take them off to do the various types of analysis. Okay, we will break for there. Just for anyone who wants to stick around and like see how it all works, you can. If you want to, just go ahead and do the analysis of all this stuff. Let me just kind of show you how it works. If you're in, and again, feel free to leave. I know some of you have to leave to get to a class. Yeah, if we are taking a building like this and we want to export it to GBXML because we want to do that same sort of analysis, what we can do is actually, as opposed to just taking the form here, we can say include the thermal properties, and that'll actually take all the work, all the U values and the R values that we put in there ever so carefully, and use those for the analysis so we don't have to reset them in the other tools. So we can do that in GBXML if you want to, or the way that I tend to do it more often now, because it's now available just as a cloud service, is I can say analyze, do a detailed analysis, and just from here, just say run the energy simulation. And what it's going to do is, based on that building and the rooms and the thermal properties here and all that kind of stuff. It's just going to take it to the cloud analysis service, and yeah, do the analysis for us. So as opposed to taking it out as a GVXML file and having to go through do the analysis over there in Ecotech, it's now just built into a service to make it a little bit easier to get to. Okay, so let's break for there.